So roughly we left off speaking about expectation and variance of continuous random variables. And if you regard continuous random variables in much the same way as you did with discrete ones, there is no such big difference. So remember that, let's say if we have a distribution between A and B, so in other words, the random variable capital X can take numbers between A and B continuously, and this is the density function by which it does so. I can imagine that this picture is just a histogram, or I prefer to think of it as a laid out matches that are of different elevations. The elevations of the matches are different at different places, but the tips of those matches, they trace this outline. And here I made the match rather very big, very fat, but it's supposed to be, in essence, this is supposed to be very thin. So from X to dx, it's supposed to be very thin. Good. So yeah, it's supposed to be very thin. So what are you in essence doing when you calculate the expected value? You are measuring the probability of that value. So the probability of that value by default is the area of this rectangle, right? So it's going, the area of this rectangle, its width is dx and its height is f of x. So that's just the probability multiplied by the value. And then you sum over all those values, over all x, which as you take the limit, that becomes the integral, right? In general, the integral, if distribution goes from minus infinity to infinity, it will be the integral of x fx dx. I hope that makes intuitive sense why that should be the case, right? Integral, by the way, it's just a fancy way of saying sum. This is just adding things up. It's just you add infinitesimally thin matches, their areas. Okay. So then we made, I think, a calculation of a few expected values. So for example, if my function is f of x equal to 2x whenever x is between 0 and 1, in other words, it's 0, the expected value is just the integral from minus infinity to infinity of x fx, which ends up being 2/3. Okay, so that's just basic integration. So here is the next example. Let's see if you can help me solve this one, right? Definitely those that came to the class last session. So suppose that I have this density function. In other words, the density function is 1 over 0 up to 1, and outside of this interval, it's 0. I want you to try to calculate the expected value of e to the x. Go ahead, do the calculation, please. Why by parts? Well, think about how you set this problem. Set it up and integrate, right? So you understand the question, right? So this is my random variable, it's e to the x. How would I figure out the expected value of e to the x?
Integration by parts.
So you think integration by parts, but why? Why do you think integration by parts? I see no need for this. That's just a tool. I mean, first of all, do you understand what's the what is the setup? That's the more important part here, the setup, and why the setup is what it should be. So George says that the answer, the expected value, is 1. No, it is not 1. No, why would I see. Thank you, David, for making that clear. Why somebody thinks it's x times e to the x? I do not see that. E to the x. What's happening, guys? Think about something very simple. What's happening? So a random is randomly picked. A number, sorry, is randomly picked between 0 and 1, and then this number is placed as in the exponent of e. Right. So what numbers are you actually going to see? The smallest number you could possibly see is e to the power of 0. Yes. E to the 0, and the largest number we can see possibly is e to the power 1. Yeah. So what is the expected number we're going to see? So it involves 2 steps, at least from our standpoint right now. It involves 2 steps. The first step is I need to know how the random variable is distributed, right? So x is distributed uniformly. We're going to talk about it, I think, today. But y, or y which is equal to e to the x, does not have to be distributed uniformly. So I begin by trying to find the probability density function for y. So the probability density function of y can be obtained from the cumulative distribution of y. So which is at a, the probability that y is less than or equal to a, which is the probability that e to the x is less than or equal to a, which is equal to the probability that x is less than or equal to ln of a. You with me, guys? Right. So I basically move. I'm not sure what's the need for cumulative distributions when you're dealing with discrete random variables. I do see that they can be useful when you're dealing with continuous random variables because of integration tricks. So the cumulative distribution, its derivative, right? Its derivative will give me the density function, which is what I need to obtain. This is y times the density function is what I need to calculate. Yeah. So the cumulative distribution of y is the cumulative distribution of x evaluated at ln a. You see how we go there? So it's just y is less than a, which means e to the x is less than or equal to a, which means that x, I take logarithms. I don't change, logarithms are increasing, so I don't change any, I don't change the inequality. So x is less than or equal to ln a, and that means that I have the cumulative distribution evaluated at ln a, the cumulative distribution of x. So then I take the derivative of the cumulative distribution for y, which means take the derivative of this. And by fundamental theorem of calculus, the derivative of capital F is little f, right? And the derivative of ln a is 1 over a. Yeah. So we have 1 over a times f ln a. Now, what is this quantity? Now, let's see about it, right? So when x is between 0 and 1, e to the x will be between 1 and e, and ln of that number, of course, will be a number between 0 and 1, which will just be 1. This will identically reduce to 1. So I have this cumulative distribution function. I have f of y equal to 1 over y whenever y is between 1 and e, and 0 otherwise. So stop me, guys, if I stop making sense, if something is and somebody says it also yields e to the e minus 1. Yes, that's what we are getting here. So the expected value of y is simply the integral from 1 to e of y times 1 over y, which is just integrating 1, which ends up being e minus 1, right? And there was no need for any integration by parts here. Good. So if you understood the idea, perhaps you will try at least set up. I don't need you to finish evaluating this. Here is a similar problem. So we have a density function. I verified, of course, its density, right? So the integral of 3x squared between 0 and 1 has to equal 1. So we have x, and this is how x is distributed. So you see that it's more likely that x takes values closer to 1 than it does closer to 0. and I want you to calculate the expected value of root of x plus 1. Well, so everyone, whoever is incognito here, I'm going to mention that, right? So you have just plugged in e to the x, and perhaps, maybe you already see why you are correct. But the question is it always going to work? We're going to address this, your concern, in a moment, right? Right now, by the very definition, what do we need to do? To calculate the expected value of any variable, I need to know its density function, and then I need to integrate the value. Let's say if this is y, I need to integrate y times the density function fy. Yes, at least from the definition. This might be an uglier integral, but I want to see if you can set it up. That's all I want. Perhaps you are absolutely right, but we have to be really careful here. Okay, so you want to do it by definition. That's. I mean, if you just integrate something, it's like you're stepping into a minefield. How do you know you're correct? All right, guys, so let's try to see it together. So first, you begin calculating. That's not so important. What is it that you imagine? So I imagine a sort of enigma machine, right? So where you have buttons like on a keyboard, and a button is randomly pressed. And when you have a function like root of x plus 1, there is, although a button was randomly pressed, there is some sort of transition from the button to some other input indicated, right? So here a number is selected between 0 and 1, but then the number selected is being processed as follows. 1 is added to it, and then you take the square root, okay? So the actual numbers that you will see popping out, so I can call this y, the actual numbers that pop out are what? Are between root of 1 and root of 1 plus 1. In other words, between root of 1 and between root of 2. Yes? So y takes values between 1 and root 2. Okay? Now I want to figure out what is a density, what is the probability density function for y, so that I can deal directly with y. That's the definition of expected value, at least, right? And I don't know it. I don't know how y is distributed. So what happens then is as follows. So I take the cumulative distribution of y, and that's only the probability that y is less than or equal to a. Yes? And that equals to the probability that root of x plus 1 is less than or equal to a, which is the probability that x is less than or equal to a squared minus 1. You agree? I just moved to the position where it's the probability x less than something. And that is just the cumulative distribution of x evaluated at a squared minus 1. Now, by the fundamental theorem of calculus, the density function for y is the derivative of the cumulative distribution for y. So I take the derivative, it's the derivative of capital F at a squared minus 1, which is the derivative of capital F is little f at a squared minus 1 times the derivative, which is times the derivative of what's inside, which is just 2 times a. Yeah? So I have that the function is 2a f a squared minus 1. Good? Now, what does it mean? It means that now I can move it. If I don't want to use a, I will use the letter y. It means that for all y where the probability isn't 0, it's going to be what? It's going to be 2 times y times f of y squared minus 1. Now, what was the function? I multiplied by 3. So 2 times 3, that's where I get the 6. Right? So it will be 2 times y multiplied by 3, y squared minus 1 squared, where y is between 1 and root 2. Yeah? And 0 otherwise. Okay, so for the y's where it's defined, that's where we get back the x and we square it. So the expected value of y is then the integral of this density multiplied by y. Hence, that's where I get y squared. And then I have the integral from 1 to root 2 of 6y squared, parentheses y squared minus 1 squared. And this integral you just can multiply out and evaluate, and roughly you will get this number. So you'll get 1.320 when you evaluate this integral. Okay? So it might be rather tedious to search to do this work. So we have y is just some function g of x. So x is a randomly picked number, and then we have a continuous function g that processes this number further. So how do I find the possibly maybe there is a shortcut for finding the expected value of gx. So here is an example, like the first example we studied. We have f is uniformly distributed over 0, 1, and we want to find the expected value of e to the x. Now, just like you did with discrete random variables, what did you do? You notice that you can just take the function, you can evaluate the particular x and work with the distribution of x. In other words, you work with the density function of x itself. So you have e to the x times the density function of x, and that amounts to integrating from 0 to 1 e to the x dx, which quickly yields e minus 1. So I did not bother finding a distribution for this new random variable. I worked with the distribution of x itself, and notice I got an answer that is correct. It's the same answer. Now, if I have root of x plus 1 as before, I could have tried to work with the original density function. Just take root of x plus 1 multiplied by 3x squared. Okay, and of course this now is a bit ugly. You need a bunch of manipulations like u substitution and whatnot. And when you carry out the u substitution, you say this is the calc 2 technique or calc 1 technique to solve it, you arrive at the same integral we just arrived at before, same integral. So why does it work? Yes, I noticed only later that you plugged in e to the x into the density function. But just like with the discrete random variables, you can work with the original probabilities of x. And I will try to explain why that's the case in two ways. Possibly that's intuitive, and possibly it's not. So this is a proposition that tells you that you can always do that. I prove it here because the proof is a bit simpler. I prove it for the case where the function is non-negative. So y is a non-negative random variable. Okay, x can take values between minus infinity to infinity, but y cannot take values below 0. And that's not a requirement for this thing to work. It's just it makes the proof slightly easier, right, to explain. Later down, I ask you to, if you are interested, to try to prove it in the general case. So first is the following thing, right? We may argue that this is just an immediate consequence of the proposition we proved for discrete random variables, right? Because I can think of a continuous random variable as a discrete random variable, but where the points are very close together. So in other words, if we go back to this picture, this line, you can imagine it's discrete, just you have many points tightly bound together. So this is the distance between them. It just has to be small. And then everything about the expected value here works just like in the discrete case. We verify that this is just an interchange of summation. It's a change of order of summation, and that's why this property worked in the discrete random variable case. Remember that the expected value of g of x was g of x times the probability of x. That was the discrete case. So that's when you are integrating, you are doing the same thing. You are summing gx times the probability that it occurs. Just the probability it occurs is the density times dx. That is now the probability. So it works very much in the same way. I will try to explain it. You just maybe a good training for Calc 3 ideas. I will try to explain this through integration. Okay. So this is why that will be the case. So we're assuming for a moment that y is non-negative. So by the definition, you calculate the expected value of y as the integral of y times the density dy, the density of y. That's why we needed to calculate this function beforehand. Now, you can translate this into a double integral. I can make this, you see, I kind of use abusive notation here, but the integral here from 0 to y, possibly I should have changed this to t. So basically the integral from 0 to y of 1 will be just y. So what I wrote here is abusive notation. Should be, if you are not familiar, some sort of t. Okay. What is then this region over which I integrate? So I call it my baking, my frying pan or a baking pan. So the baking pan is, you can read it as follows. So you see, that's where the slices are made. So we have y varying from 0 to infinity, and x varying from 0 to y. Right? So what does it mean? It means that, well, for a fixed y, here is for a fixed y, my interval over the x-axis goes from x equal to 0 to x equal to 1. So I see horizontal slices. If it doesn't make sense, guys, that means you might have not remembered your Calc 3. Right? So I see horizontal slices. Right? So basically, this tells you how to calculate the volume of a cake. If at some point, I mean, I can give you a review of that after the class if you want. So the cake is sliced horizontally. Y goes from 0 to infinity, and for each fixed y, the slice is from x equals 0 to x equals y. So I see that the shape of my baking pan is triangular. I am going to redescribe this shape by vertical slices. Okay, so the same baking pan, but with vertical slices. So how do you describe this region by vertical slices? So you notice, because it's an infinite triangle, I can make x go from 0 to infinity. And if x goes from 0 to infinity, this is y equals x, right? So then the vertical slice will be of infinite length. So it will be y goes from 0 to infinity for every fixed x. So as a double integral, we have that the above expression equals to 0 infinity, x to infinity, fy dy dx. Now, what is this quantity here? This quantity here, it's, look at it, it's the probability that y is bigger than x, which I can write as the integral of probability y bigger than x. So I wonder, guys, as I'm talking about it, how much sense am I making? 0 to 1. Would you say 0? 0, yes? So one person says 1. Well, that's very nice of you, right? And for others, am I making 0 to 1? 0.6. Do you understand why I call it a baking pan? I wonder, you think, well, I'm just crazy, right? Why am I calling it a baking can? No. No, okay. Should I review double integrals before I continue? Let's see. I might say a few things here, and maybe that will help, maybe. Although that's the problem, you see, guys, I do not know how much. This is the way I describe double integration. Okay, so suppose that Aunt Jemima bakes you a cake. Okay, this is the cake that she used. So the cake is rectangular in shape. So you see on the x-axis it extends from AB. On the y-axis it extends from CD. Yes, and what do you observe about this cake? You want to calculate the volume, for example, right? And you want to calculate it by slicing it up and having cylinders. So at some point x, you make a slice, right? As you make a slice to the point x, you see that here you have here is the cut. You get what? You get an integral. You get an integral where if the crust of this cake is fxy, it's the integral of y going from c to d of the function f evaluated at x0 and y. Do you follow? That's the cross-sectional area. That's from Fubini's theorem. If I cut this cake this way, then the area of this slice is just the integral of this function, which is the crust function, where x is fixed at x0 and where y goes from c to d. It's a one parameter integral. Yes? Good. So again, guys, you see that that's the terrible problem, is that I think I can explain Calc 3 pretty well to you, but I will have little time. So you kind of have to make do on your own, or talk to me and talk to you, you know, right? So I'm sorry for this handwriting here, but you see, the way I describe this, this is the area of the cross-sectional cut. You see what I'm pointing at? From C to D, x, y, dy. That's where the cut is made. The knife cut the cake at the point x. So that would be the integral there. Yeah. And then to find the volume, I just have to think about it, right? The slice, if I make a slice x to dx, then I have like a loaf of bread, a piece here, a loaf of bread. And if the distance is very small, if x to x plus dx are close by, then it's essentially a cylinder. In other words, its face has the same area both front and back. Of course, look at it. You see, this part does not have the same area as this part. But if they are very close together, then it's essentially a cylindrical cut, where the volume is given by this area multiplied by dx, which is fully expressed as a double integral from AB CD, right? Now that's when the cuts are along the parallel to the y-axis. I could cut the cake parallel to the x-axis, and then the inner integral will be between a and b, and the outer integral would be between c and d. Okay, and this is and the bottom here is what I call a frying pan, because you see that's where that's the cutter that determines where the cake is sitting, right? And for the example I was dealing with here, this is my cake. My cake is not over a rectangular frying pan. The cake, I recognize it based on this integration. From this integral, I recognize it's like I'm Sherlock Holmes, and I'm doing investigative. I'm doing an investigation, and I say, okay, I can figure out from both integrals the shape of the frying pan in which the cake was made. Yes. So the cake. Here y goes from 0 to infinity, and x goes from 0 to y, which means that y is extending here. And then for each, the slices were horizontal. For each fixed y, that's what this means. For each fixed y, x goes from 0 to y. X is starting at 0 and goes all the way to here. That's where you see the y. Good. And then I decide what happens if I cut this cake by vertical slices. If I cut it by vertical slices, then the description is that x goes from 0 to infinity, and y goes from x, y equals to x, to infinity. You agree with me? I hope I made some tiny amount of sense. If not, again, guys, I'm happy to try to, after class or some other time, to try to go over the integration methods from Calc 3. So I'm sorry if not everything is clear. So what you have is then you have this integral, and this inner part of the integral just means that y is bigger than x. Yes, I'm changing just the order of integration. I just have to know how to do that, not only for rectangles, but for other shapes. In this case, it's triangular shape. And I realized that I was cutting a triangle, an infinite triangle, because, you know, it goes forever. By horizontal cuts, now I'm cutting it by vertical cuts. So I realized that it's just the integral of the probability y bigger than x dx, which it's just a letter, right? So this is the integral from 0 to infinity probability that y is bigger than y dy, which is the same as the probability, that's what y is, that g of x is bigger than y, which is the integral from 0 to infinity. And this means what? It means I integrate over all x such that g of x is bigger than y. This is basically what I observed, okay? So x such that g of x is bigger than y, right? So the way I switch things around, and now I end up with integral from 0 to infinity of the integral x such that gx is bigger than y, fx dx dy. And I'm trying to understand what is this? What sort of thing is this? Now think about it. If this is the graph of g of x, and this means, okay, here I fix a y, fixing a y, I then have to integrate over all x's such that g of x is bigger than y. Look at it, right? So you see the picture. If this is g of x, here is a y, and then I have the slice, and what are the x's such that g of x is bigger than y? So g of x is bigger than y over here. G of x is bigger than y over here. So here in that particular picture, those are the this integral is over this region plus this region. Okay. What I'm explaining is rather technical, but once you start, writing it down, thinking about it, it should be trivial. So look at it. I described cutting a I went from cutting a triangular cake to suddenly cutting a cake where the frying pan is between the x-axis and y. So the frying pan is very complicated. It's this shape, right? It's the x-axis together with this curve. So it's much easier to represent this integral by vertical slices, right? Which are what? So changing the integration again, this means I go for x between minus infinity to infinity, and y goes from 0 to g of x. Okay, I get this integral. And this I can simplify to the integral from minus infinity to infinity, gx fx, which is the statement of our theorem. That means that I can keep the distribution of my original random variable x and just multiply it by g of x. I hope you understood at least a quarter of what I said. Yes? What about you, Jeremy? You look like you were tortured, like I tied you to a chair and my God, right? Poor little Jeremy. The light even went out. Exactly, right? So g of x represents, so little fx. What does little fx represent? It represents the density function for x. G, you might prefer to write g of capital X. So what happens is this: a random variable is generated, a number is generated, and then you plug it to another function. So for example, g of x in the example here, it was e to the x, right? So x is generated randomly, and then you take this number and place it as the power of e. So right. So the general situation, guys, is that this does not have to, g does not have to be non-negative. It could be anything, right? So the general situation is that the expected value of gx is just the integral from minus infinity to infinity, gx times fx, where this is the density function, and this is just the transformation that x undergoes. Let's try to see how this idea is being used. And then if not, we can return again to the problem, okay? So I hope this might be slightly more interesting than this overly theoretical discussion. So a stick is of length 1. And that means one stick, it's its own length. And it's split at a point x that is uniformly distributed over 0, 1. In other words, it's likely that the stick is cut anywhere, equally likely, right? Anywhere between 0 and 1. So determine the expected length of the piece that contains the point t, which is between 0 and 1. Let me explain what I'm talking about. So imagine that that you have this strand, the stick, and somewhere on the stick is a special point, something you care about. Okay, this point t is fixed at the stick. Now the scissors will randomly cut anywhere between 0 and 1. So a cut will be made, okay? And then you discard the piece that contains, that does not contain the point t. You just keep this piece, okay? and you want to know what do you expect, what's on average is going to be the length of this piece. So you understand what I'm asking? Yes, guys? See if you can figure it out, and I'll help you. If you want afterwards a review of integration, I can try to help you. I saw the notes. All right, let's talk about it. Okay, so you understand what happens. The length of the piece that contains the point t, I write it as L sub t of x, where, well, what is it? It's if the cut, as I show in the picture, is less than t, it's going to be 1 minus t, right? And if x is bigger than t, if x is cutting it over here, then I take this piece. So it's either 1 minus x or x, depending on where I cut it regarding the point t, right? So the expected value of LT accordingly, I don't have to figure out I don't have to go and figure out the density function for L. I can work with the given density function f based on that theorem. So that is, I can integrate from 0 to t, and if I integrate this function from 0 to t, then I am using this part, so it's 1 minus x times dx, plus the integral of this function from t to 1, then I'm using this part, okay? So do you have at least a sense of how I get this integral, guys? Yeah? Cool. I mean, I can see a few of you, so you can shake your head. So once you integrate, you will see that what you're getting is 1/2 plus t times 1 minus t. And you notice that this expected value is maximal whenever t equals to 1/2. Okay? If t equals to 1/2, this number is as big as it can possibly be, and that will give us maximal expected length. So here is a silly example of where such considerations might be potentially useful. Okay, so it's an optimization in constructing. So yeah, so I have the place where an accident occurs is a random variable x, and this is the probability density function. So imagine that you have a road, which I drew as a straight line. Yeah. So that's the road. So the highway begins from some point 0 to where it ends, it's the point 1. And the question is, if this is the likelihood of the accident, could you decide what's the best place to build a hospital so that you know, the ambulance will take less, so that the accident will happen as close as possible to the hospital, so there is faster response time? Just set it up. You don't need to evaluate it. If you could set it up. Two-thirds. All right, let's see how I set it up. So most importantly is setup, right? So an accident occurs somewhat randomly, but you know, it means what? 2x means that it's more likely to occur near the end of the road. Yes. So it's more likely that so two-thirds might be a possibility, right? Because it's not likely to be exactly in the middle. You might want to move the hospital closer to this area, to this region, because that's where I guess the road is more dangerous. So an accident occurs somewhere, and suppose you constructed the hospital at some point Q. It's just pretty much like the same previous problem. So so then what is the distance to the hospital, right? dq of x is the distance to the hospital. So if the accident occurs to the left of the hospital, then it's q minus x is the distance. If the accident occurs to the right of the hospital, then it's x minus q. And so I integrate from 0 to q. From 0 to q, I integrate this function times 2x. And from q to 1, I integrate this function times 2x. And when I go through, right, I get that my expected value, because so 2/3 I do get there, but I have other stuff. So the expected value, I simplify it as simply E of Q. The expected distance to the hospital is 2/3 minus Q plus 2/3 Q cubed. Okay, if I calculated my question correctly, that is the answer. Now I want to see where is this minimized. Okay, so where is it minimized? What I do is I take the derivative of this function, and the derivative of this function I set equal to 0. So I have 2q squared minus 1 is the derivative. Now, if you remember Calc 1, I draw this interval. I draw the points at which this is 0, the minus 1 over root 2. This, of course, is not useful, but I'll draw it anyway. And 1 over root 2. Okay, and then I see where I have the minimum, right? So notice if I go from 0 is somewhere here, towards 1 over root 2, I am decreasing the distance. And then after that, I'm increasing the distance, which means this value, 1 over root 2, is my minimum, right? So I should construct the hospital at the point 1 over root 2. And when you plug those points in here, you would know what's the expected distance. But I have to build it at the point 1 over root 2. So in other words, 1 over root 2 of the distance from the beginning of the road. Good. There is one more example like this. I might skip it. Try it on your for yourself. This has to do with trying to not be late and also trying to not come too early. So this will be the last example, but I will go to my next lecture notes. Let's talk about uniform random variables. So we begin studying the distributions here. So we have the uniformly distributed random variable over AB. And the density function is as simple as it can possibly be. It's equal to the same value everywhere. It's equal to C over the full interval AB. And clearly C has to be 1 over B minus A, because the area of this rectangle must be equal to 1. Now, the cumulative distribution, it's just the probability that x is less than or equal to t. It ends up being the integral from a to t of b minus a, and it becomes therefore t minus a over b minus a. And this is the cumulative distribution for any value x. Here is a picture of it. So one thing about uniform random variables, that's they are analogous to picking numbers randomly. So if you had 5, say if you throw a dice, for example, right? You throw a die, it has 6 faces. If each face is equally likely, then you see that each face has probability 1 over 6, same probability. So uniform random variable is in that sense similar. There is no preference to one set of numbers over another set of numbers. And if you realize, then the probability that that x belongs to some interval I, where I is a subset of AB, it's just the same as the length of the interval divided by the total length. Okay, so I don't even need to go to integration to figure out the probability. It's just proportional length. So here is an example. See if you can carry out the calculation. So we have x. It's uniformly distributed from 0 to 20. I want you to calculate the probability that x is between 5 and 10, and the probability that x is bigger than or equal to 5. So Eli, you mean A is 5 over 20, yes? Yes, yes, both are correct. Both are correct. So very simply, that x is between 5 and 10. It means that my interval is what? The interval is of length 5, and the relative length of this interval is 5 over 20. And the relative length of this interval, you can just say this: it's 20 minus 5, or so 20 minus 5 is 15 over 20, or 1 minus 5 over 20. It's the same thing. Okay, so this is 15 over 20. Here I wrote integration, but I hope you understand very quickly that you see it's just clear by the density, by everything. It's clear that the 1 over 20 means 1 divided by the total length. So it's clearly the length of the interval divided by total length. All right, here is another, hopefully also very simple question. So theta is uniformly distributed. We select a random angle. That's what this means, right? I select a random angle between 0 and 2 pi. I want you to calculate the probability that sine of theta is less than 1/2. Two-thirds. All right, let's see. So what's happening here? I need the sine of theta to be bigger than or equal to 1/2. What it means is that my angle has to be, well, sine grows and then decreases. So it's either first or second quadrant, right? Either first or second quadrant. And so theta is bigger than or equal to pi over 6. Pi over 6 is the first time sine is equal to 1/2. And then it continues growing until it's pi over 2. Then it begins to decrease until it's pi or minus pi over 6, which is it decreased to 1/2 again. So from pi over 6, where it's first 1/2, until pi minus pi over 6, the second time it's 1/2. That's the that's the interval size that we go over. That's when sine is bigger than 1/2, right? And then the length of that interval is 5 pi over 6. Yes, I'm calculating it the other way around. It's easier to have a full solid interval this way. So what happens then is sine bigger than or equal to 1/2 is the probability that theta is between pi over 6 and 5 pi over 6. The length of this interval is 4 pi over 6, and the total length of the domain of theta is 2 pi. So I need to measure the relative length of my interval, which becomes 2 over 6, which becomes 1/3. Yes? So 1/3 is the probability that sine of theta is bigger than 1/2, which means the probability that sine is less than 1/2 is 1 minus the probability it's bigger than 1/2, which is 2/3. Good? Here is another problem. Hopefully also simple. So you have trains and they run every 10 minutes. Let's say 2 to 10 to 20 and so on. If your time of arrival is between 2:05 and 2:35, what's the probability that you have to wait less than 5 minutes? Isabella, you're invisible today, are you? And John? Oh, don't be like me. All right. So that looks right to me, 3, 8, if I remember. So here is how I set it up, right? I don't like that it starts at 0, 5, so I make x plus 5 my random variable, right? So x plus 5 is my time of arrival, where x is between 0 and 30. That's out of convenience. I prefer, 0 to 30. So then you wait less than 5 minutes if x plus 5 is between 5 and 10, or between 15 and 20, or between 25 and 30. It's impossible to arrive exactly at 35. Okay, so yes, so yes, so this is the only possibility. So now all of them are intervals of exactly the same length, and the length for x is distributed between 0 and 30. The length is 5. X is between 0 and 5. So it's 5 times 3 divided by 30. Right? So yes. So so it's 3. It's 5 times 3 divided by 30. Make sense? Why? Each interval is 5 over 30, and we have 3 of them. So it's the probability is actually 1/2. All right, guys. Would you have time for the next problem? It's pretty interesting. Bertrand's paradox. It will take me more than, I think, it will take me probably 10 minutes to explain it. Or if you want to think about it and then, what do we do, guys? Are you going to stay with me, or you want to leave? We have essentially what? We have 2 minutes. So Bertrand's paradox, yeah, German. No? All right, so what we'll do is we'll talk about this paradox next class. Perhaps read this and try to solve it on your own. Yes? Well, I now understand, thanks to you, Norosima, and other people, GGWP. What is GG in WP? Good game, well played. Okay. Learning so many new vocabulary, huh? Chess lingo? You're in chess class? Ah, sorry, I understand. I thought you're going to another. Okay, so anyhow, guys. So if you want to, good good night. If you want to, we can talk about integration. If you are rusty on it, okay, let me know. Take care, Jeremy. Yes, John. Have a good one. TTY. God damn it! Yeah, you have to make it called. What is it? Thank you. What is TTYL again? All right. Yeah. Okay. So if you God damn it, you already invented a new language. What is it? HMU? Have what? God damn it! What is it? I'm sorry. You're actually awful. Yeah, so if you want to, we can discuss integration. So all of you that want to go and sleep, good night. And if you want to, we'll discuss integration later. All right, so integration. So I'll stop the recording. You know what? So is it stop recording? Yes.